In this video, we're going to be talking about the factor theorem and the remainder theorem. These two theorems ultimately kind of point us back to polynomial division, which is going to be the real algorithmic focus of this lesson. So what we're going to talk about today is first polynomial long division and synthetic division. Long division is kind of cumbersome, just like we imagine long division to actually be. But the one thing that's really nice about polynomial long division is that we can do it with anything. If we've got a linear divisor, quadratic, cubic, whatever. Synthetic division is really fast. It's really efficient. And we're actually going to spend the bulk of the course using synthetic division just for breaking down polynomials. The one drawback to synthetic division is that you can only divide with linear factors. Okay, so we're going to kind of talk through that today. Then we're going to use polynomial division to make inferences about the roots of a polynomial. And from there, we'll be able to make inferences about the factors of a polynomial. Just to give you an idea of this like connection, it's really not that fancy a connection at all. If I've got a polynomial, and we'll call it p of x, let's suppose that p of x has a root at x equals 2. Then if I were to factor out p of x entirely, then what would happen is, in that factorization, since I've got a root at x equals 2, there's going to be a factor at x minus 2. So somewhere in that factorization, I would have an x minus 2. Okay. What we're going to do is kind of use this information throughout the lesson, but for right now, I just kind of want you to understand that basic connection. So on this page, we've got polynomial long division, and if you can hear my son in the background, he's really not excited about getting into it. That's okay, though. Here's my poorly written procedure, just by virtue of my penmanship on this screen. Instead of leading coefficient, I made a mistake here. It should be leading term. I can understand how that would create some confusion. So what we're going to do is first we're going to divide this thing right here by this thing here. This, because we're dividing by this thing, this is our divisor. And this is what we're dividing. This is going to be our dividend. So in familiar ilk to long division, which is what we're used to seeing, we've got this, it's kind of like a radical. I don't really know what the actual mathematical term for it is. I don't think there is one. And so we've got x cubed. We'll just put a 1 there. 4x squared minus 5x minus 14. I'm definitely going to have a few more videos for this posted in the module. And I'll obviously give credit to the content creators for that, just to make sure that I'm being ethical. What we're going to do is basically do these first 3 steps and then rinse and repeat. And we're going to continue in an iterative way until we finished with our algorithm, which, since our divisor is a first degree polynomial, since it's a linear factor, we are going to be able to stop when we end up with a constant. In the same vein, if we had a quadratic divisor, we would be able to stop when we have a linear. Ultimately, when the last thing that we end up with is a lesser degree than our divisor, we're finished. So first, we divide the leading term of our dividend by the leading term of our divisor. So we start with 1x cubed, and we're dividing this by the leading term of our divisor, which is 1x. So the x's cancel, and I end up with just x squared. Right? I like to put my x squared, all of my terms of my polynomials just kind of lined up so that I don't get kind of lost in the sauce. So that's the first step. Now the second step, we distribute this result into the divisor. All right, so we distribute the x squared into the x, we get x cubed. And then we distribute the x squared into -2, and we get -2x squared. All right, now we do the third step, which is subtract. So what we're going to do when we subtract, we're actually going to negate everything. Okay, and then we're going to add. So now we have 1x cubed minus x cubed. That's a 0x cubed. This is a great sign. When I'm ratcheting the degree down each and every time, whether it be by 1 or by 2, depending on what my divisor is, this is a good sign. So now I'm going to add the 4x squared and the 2x squared, and I'm going to get 6x squared. And then just to make sure I don't lose my place, I'm going to drag down the remaining terms. Okay. Great. Now we've done step 3. Now we rinse and repeat. So now we do the same thing we did before. We know that we're on the right track because we end up eliminating this x cubed term. That's great. So now we perform division of the leading terms. This is my new divisor. So my new divisor, or my new dividend, I'm sorry, is going to be 6x squared. So I take 6x squared and I divide it by 1x. The x cancels the x squared. I'm left with 6x. So now 6x goes on top of the unnamed thing. And now, just like we did before, we take that 6x and we distribute it to the x minus 2. Again, this is not going to be the only video for this that's going to be posted. I'm absolutely going to have 1 or 2 more examples. So I get 6x squared minus 12x. And now I negate and add. So we negate both of these terms. We add them, 0x squared. We're doing great because these remove each other. And so now I end up with 7x minus 14. Okay, now we are ready to rinse and repeat. Since I ended up with 7x minus 14, that means I'm going to be in the last step because I have a linear divisor and I have a linear term here as my new dividend. So I take the 7x, divide that by x, and I get 7. That's great. So I've got a constant term. So now what ends up coming out at the very end is my remainder. So I don't need this anymore because I know the remainder is coming, which means I'm done when I get to the remainder. Now I take that 7 and I distribute it to my divisor. And I get the 7x minus 14. And now I negate both terms and I get 0x, that's great, and 0. So now 0 is going to be my remainder. We're done, we're finished. Now, a remainder of 0, that's a great sign. What that communicates to me is that the original dividend, this original polynomial, is evenly divided by x minus 2, and what I'm left with is this quadratic. So effectively, what I can say here, so first off, let's address the vocabulary of this. So I performed this division and I ended up with x squared plus 6x plus 7 with a remainder of 0. This term here I call the quotient, and my remainder is 0. Now, since I actually had a really nice division, what I can say at this point, I'm going to go ahead and just erase. I've got my division here, so that's what we needed to see. What I can say at this juncture, since I have a remainder of 0, and again, this only happens with a remainder of 0, because what that means is the division was really nice. If I divided this thing by x minus 2 and I have a remainder of 0, that tells me that x minus 2 has got to be a factor. And after I factor out this x minus 2, I end up with x squared plus 6x plus 7. Okay, so we'll get into that in particular. For right now, I just want you to wrap your head around the polynomial long division algorithm. Now, what I'm going to do here, I'm just going to go ahead and show you the synthetic division just as it works. So the way that this is going to operate is I'm going to list all of my descending coefficients up top. So I've got 1, 4. I'm not worried about the x terms or anything like that. I just need to make sure they're in order. Okay, so I need to make sure the polynomial is written in standard form, where you've got like x cubed, then x squared, then x, then constant. If I don't see a term there, I need to make sure that there's a 0 in that place. We'll talk about that. So now what I'm going to do is I'm going to take my divisor and set that equal to 0. I'm going to add 2 to both sides. So x equals 2. So now, here's what I'm going to do. I'm going to make a little box, and inside that box is going to be the 0 of that divisor. So the 2 goes in that box. Now, I want you to just kind of follow along with the process. Just put your eyeballs on it. I think you're going to find that it's not terribly confusing, but it's really weird to write it out. So I just want you to observe it. We're going to talk more about it. First thing I do is I take the leading coefficient and I drag it down here. Now I take the term that's down here, multiply it by the number that's in the box, and I place it here. So 1 times 2 is 2. And now we add. 4 plus 2 is going to give me 6. Now I do the same thing. Take the 6, multiply it by the 2, I get 12. And now we add. Negative 5 plus 2, that's going to be 7. Now I take the 2, or I'm sorry, take the 7, multiply it by the 2, I get 14. And now we add. Negative 14 plus 14 is 0. So this is my remainder. And what I'm left with is this, since I took a cubic and I divided it by a linear, what that tells me is this now is a list of coefficients for a quadratic. So now I've got 1x squared plus 6x plus 7. This last box is always going to be my remainder. So this new list of coefficients is going to be a polynomial of degree 1 less than what we started with. So this is going to be my quotient. So my remainder is right there, and this is going to be my quotient. Okay, we're going to see more examples of synthetic division, and we're going to use it, in a very applied way. When the remainder is 0, obviously we have a really nice division. We have a good thing going. Okay, so why did we do all of this? So there's 2 things to keep in mind that this lesson is sort of built around. The first of which is the remainder theorem. And the idea here is if I have some polynomial of degree 1 or greater, and c is a real number, if I were to take p of x and divide it by x minus c, whatever that remainder is p of c. Effectively, what I'm saying is, if I take some polynomial and I divide it by x minus c, I'm going to get some remaining thing. In particular, I'm going to get a quotient and then like a remainder tacked on. That remainder is that polynomial evaluated at c. That's all we're saying here in the remainder theorem. And I'll drive this home a little bit. And then the factor theorem is what we already talked about here. If I've got some polynomial and c is a root of the polynomial, so x equals c is a root, then what's going to happen is x minus c is a factor of p of x, which is what we talked about here. If I have a nice division with a remainder of 0, that thing I divided by must be a factor. And the quotient is going to be whatever's left after I factor out that divisor. Okay? Now, let me explain a little bit more about the remainder theorem later on in this lesson. So now, what is the point of any of this? So from the previous slide, what we found was, so now I'm asked to find the horizontal intercepts of this polynomial. Well, as we saw before, this polynomial had a factor of x minus 2. Now, how did we know that? Well, we're just going to go ahead and assume that we know that from the previous slide. And so what I know is x minus 2 is absolutely a factor of this thing. And if I were to factor it out, then this is what I'd have. It's not obvious just from looking at this that these factors come out of it. It's not obvious. There's no technique of factoring that I can think of that would help me to figure out what that, like how to get from this step to this step. I have no idea. But we're going to kind of start with training wheels on. So for right now, it feels like magic that x minus 2 is a factor, but it's important that we have that. Now, by the zero product property, what we have is, since x minus 2 is a factor, I'm going to use the zero product property and set x minus 2 equal to 0. And now I know that one of the horizontal intercepts is going to be at 2. So for my horizontal intercepts, I already know that 2, 0 is going to end up being one of the factors of this, or I'm sorry, is one of the horizontal intercepts of this polynomial. Now I've got these two things that are left. So what I'm going to need to do, and I know that there's going to be two things because it's quadratic, I've got to set this equal to 0. And I've got to solve this quadratic equation. Now from 3.2, we're going to try factoring first. I'm going to multiply 1 and 7. Can I think of multiples of 7 that add up to 6? I'm not going to be able to do that. So I'm going to have to use quadratic formula. So I'm going to use the quadratic formula. X equals, remember that A is 1, B is 6, and C is 7. Negative B plus or minus the square root of B squared minus 4AC. I should be very clear here. It looks like I made a 2 when I actually made a 7. All over 2A. So I'll give you a second to compute this 6 squared minus 4 times 1 times 7 on your own. What you should get after that, and I'm only doing this for tidiness so that I'm not using a bunch of space here. I should get 8. That turns into 36 minus 28. And now I'm going to go ahead and reduce that. I'm going to simplify that square root of 8. If you don't mind, I'm going to use the factor tree. 2 and 4, 2 and 2. There's a pair of 2s. There's a 2 left under the radical. If you need to review this particular thing, I would really take a look at the 3.2 module. Okay. And now what I'm going to do is factor out a 2 from the numerator. So I end up with negative 3 plus the square root of 2 over 2. These 2's cancel. And so now I get x is negative 3 plus or minus the square root of 2. So now, for my horizontal intercepts, clear out all of this. So now for my horizontal intercepts, I've got negative 3 plus the square root of 2, 0, and negative 3 minus the square root of 2, 0. Now, I don't know about you all, but I certainly would not be looking at this thing directly and immediately say, oh, x definitely has to be a 0 of that. I would not be able to do that. I don't have that kind of talent. If you do, that's awesome. This chapter is going to be incredibly straightforward for you. But I wouldn't be able to do that, much less see these two guys hanging out in there. I would have no idea. So again, it feels like magic that we know this x minus 2 is a factor. What we're going to do in 3.5 is we're going to come up with ways, we're going to use a technique called the rational zero theorem to find what that first 0 is. And when we find that, then we have a little bit of the magic already there. But for right now, I've got to give it to you. I have to give you a factor or a root. That's kind of the training wheels element of what I'm talking about in this lesson. Now, let me show you another sort of example of synthetic division. And this is going to help kind of set up the what we were talking about before with the remainder theorem. Again, what the remainder theorem is stating is if I took a polynomial and divided it by x minus c, that remainder would be the same value as if I were to plug c directly into the polynomial. So let's just keep this in mind. So this is x minus 3. So in my polynomial remainder theorem, I'm saying x minus c. So in this case, I'll just go ahead and say c is equal to 3. Because I have x minus 3, it was in the same way, it was x minus c. we see that c is going to have to be equal to 3. Let's go ahead and define this polynomial to be p of x, and we'll say 5x cubed minus 2x squared plus 1. What the remainder theorem states is when I plug 3 into this polynomial, what I get out is the remainder if I did this division. So let me convince you of that. So we're going to go ahead and just compute p of 3 here. So I get 5 times 3 cubed minus 2 times 3 squared plus 1. So 3 cubed is 27. 5 times 27 is 135. 3 squared is 9 minus 18 plus 1. 135 minus 18 is 117. Plus 1 is 118. Okay, so now what does this 118 even mean? Why is this even helpful? So it's not obvious why it's actually helpful necessarily. It's just kind of a thing that feels like it's floating out in space. Okay, again, I don't know why this is helpful, but you'll see. So let's just hang on to that 118. Now what we're going to do is we're going to list off the coefficients of this polynomial. So we've got 5x cubed minus 2x squared. Observe that there's an x term missing. So I'm going to say 0x. It's really important that I do that. So I'm going to list off my coefficients, including that 0. And now, my c value is 3. So what I'm just going to go ahead and do here is in my box, I'm going to put 3 in the box. And just for, tidiness, I'm not going to do a whole lot of color coding here. Take the 5, drag this down, multiply it by the 3, I get 15. All right, negative 2 plus 15 is 13. Okay, take the 13, multiply that by the 3, I get 39. 0 plus 39, well, that's 39. All right, 39 times 3. That's going to be 117. 117 plus 1, that's 118. This is the remainder of the polynomial. Now the 118 makes sense. Basically, what I did was I found a way to plug 3 into this function by secretly doing division. Now, here's the thing. I'm not asking you to evaluate. I'm asking you to actually do the division. So what happens is this 5 is now 5x squared in my quotient. So this 13 is now in front of the x, and this 39 is my constant. That's my quotient. And now my remainder, what was left? Well, that's going to be this number here. That's going to be 118, which again, if I really wanted to find this, I could just plug 3 into the original polynomial, and I'd get the remainder that way. This is what the remainder theorem basically points at. Obviously, this example is really helpful as well because you see what to do with a 0 as a coefficient for a particular term. So that's really helpful. Now, for this one, what I'm really asking you to do here is evaluate p of negative 3. Effectively, what I'm saying is, another way to think about this problem is I'm saying, all right, well, what is the remainder of 2x cubed minus 7x plus 3 over x plus 3? That's really what I'm asking for here. So let's go ahead and figure out what that is. And I think you're going to find it's actually easier to do synthetic division than it is to just plug the number in. So p of negative 3, so negative 3 goes in my little box. My coefficients, I've got a 2. I don't have an x squared, so that's going to be a 0. And then I've got my linear negative 7, my constant 3. Drag my 2 down. 2 times negative 3 is negative 6. You guys are going to get really fast at this, by the way. Negative 6 times negative 3, that's 18. Okay, negative 7 plus 18, that's 11. Times negative 3, that's negative 33. That's a 3. And then I get negative 30. So now, p of negative 3, I don't need this stuff anymore. I was just asking you to evaluate what p of -3 is, so I get -30. I feel like this is kind of an easier way to plug the number in instead of like, fiddling around so much with all of this arithmetic. Sometimes this arithmetic can be where mistakes are made, and that's a bummer. I really like synthetic division because it minimizes the addition, subtraction, multiplication, and division. So now we're getting to the real deal here. We're getting to the really important bit. So I'm telling you that we have a horizontal intercept at 1/2. I want to find the remaining intercepts of this polynomial. So something else that's really helpful here is that x equals 1/2 has a multiplicity of 2. That's going to come into play here. Ultimately, what we're trying to do is take this polynomial and factor it all the way down, and then we're going to set each of those factors equal to 0, and we're good. So what we want to do is get down to those factors. Since the polynomials of degree 4, we know that there are going to be 4 factors for this thing. So let's just find out what they are, and we'll fill them in as we get them. Okay. 1, 2, 3, 4. Okay, now here's something that's pretty neat. Right out of the gate, I've already told you 2 of them, which is pretty awesome. I told you that x equals 1/2 is a root with multiplicity of 2. So if x equals 1/2 is a root, x minus 1/2 is a factor. And since it's of multiplicity 2, it's actually a factor twice. So that's big. All right, so now let's go ahead and apply this information. So now let's do some synthetic division, and we're going to be dividing by 1/2. So we list off our coefficients. And we've got 1/2. All right, so we drag our 4 down, take 4, multiply it by 1/2, I get 2. -4 plus 2, that's going to be 2, -2. Multiply that by 1/2, I get -1. -11 minus 1, that's a -12. Multiply that by 1/2, I get -6. 12 plus -6 is going to be 6. Multiply that by 1/2. Something went wrong. See, here's the thing. I should end up with a 0 here because I know that this is an intercept. So something went wrong. Oh, you know what it is? I put a 3 instead of a -3. That was silly. 6 times 1/2 is 3. Look at that. 0. That's exactly what I wanted. So now what I end up with is 4x cubed minus 2x squared minus 12x plus 6. And I know that x minus 1/2 is a factor of that. Now from here, what I could do, honestly, is I could just factor this remaining polynomial. It's grouping, and it is actually going to be really nice with grouping. But I haven't really used this multiplicity of 2. I haven't gotten all the traction out of that yet. So now what I'm going to go ahead and do is use it again. But now I'm going to use it on this remaining polynomial. Let's get the full traction from this thing. All right, so now I drag the 4 down. 4 times 1/2 is 2. That's a 0. I guess that's nice. 0 times 1/2 is 0. I get -12, and I put an x in there for whatever reason. That was silly. -12 times 1/2, that's a -6, and I get 0. That's tremendous. So now what I have is x minus 1/2, x minus 1/2, and then the remaining 2 factors are going to be 4x squared minus 12. So from here, if you don't mind, I'm going to go ahead and get rid of my first synthetic division. Again, this is we're really interested in tidiness here. There are 2 factors that are hiding in 4x minus 12 that I need to find. And it's not obvious what those are exactly. First thing I'm going to do is factor out a 4. And so I get x squared minus 3. Now, from here, believe it or not, if you remember the difference, there's a couple different ways you could go about this. You could use quadratic formula to solve this. You could say a is equal to 1, b is equal to 0, and c is equal to negative 3. That's fine. But technically, I can use difference of squares factoring here. And I know it's kind of a weird thing to think about because, well, 3 is not a perfect square. But think of it like this. There is a number which, when I square it, I get 3 exactly, and that's the square root of 3. So now I can actually break this up into two factors, x plus the square root of 3 and x minus the square root of 3. Now, if you used quadratic formula, that's fine. What happens is you ended up with you'd end up with your roots at negative square root of 3 and square root of 3 respectively. If you didn't do that, that's fine. So now check it out. So I've got my 4. There's going to be a leading coefficient of 4 for whatever that's worth. And then I've got my x plus the square root of 3. And then x minus the square root of 3. This is awesome. So now what I get to do, I've completely factored this thing without doing any actual factoring, which is nice because sometimes it feels like that's all we do anymore. So now keep in mind, what I want to do is find the other intercepts. So I already know that I've got one of those horizontal intercepts at 1/2, 0, because that's what we were given. Now I'm going to set each of these remaining factors equal to 0. Okay, so I get x plus the square root of 3 equals 0. If I subtract square root of 3 from both sides, I get x equals negative the square root of 3. And then I'll do the same thing with this. I set x minus the square root of 3 equal to 0. Add square root of 3 both sides. And now I get square root of 3, 0. And now what we've done is I gave you, I gave you a root. I had to give you a root. I had to give you something to start with. And you broke down this polynomial in its entirety to get into all of its linear factors. That's what the rest of this chapter is going to be. And what you're going to find is I'm going to give you less and less as time goes on. All right. For this problem here, what you're going to need to do is use techniques to find all of the rest of the zeros and factor the polynomial. So I'm telling you that one of these is at c equals 8. I'm telling you that. So now what you need to do is keep breaking down this polynomial. Go ahead and pause the video and try this on your own first. Okay, so I know that 8 is going into the box for synthetic division. And I'm going to list these off, my coefficients. So I get 1, negative 24, 192, negative 512. Goodness, straight lines are hard. So drag the 1 down. 1 times 8 is 8. Negative 24 plus 8, that's negative 16. Times 8 is going to be negative 128. All right, so then I end up with 64. 64 times 8 is 512. It's going to be a remainder of 0, thank heavens, because that's what they told us it was, so that's good news. So now I know one of my factors is going to be x minus 8. Because 8 is a 0, I have a factor of x minus 8. And now I have 1x squared minus 16x plus 64. All right. Now, here's what's really cool. What I could do from here is like try and see if 8 is of multiplicity 2, blah, 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 blah. I'm just needing the factors. So all I've got to do here is now factor this trinomial. Go ahead and factor this trinomial. I'll give you, go ahead and pause the video and factor this on your own. Okay, so what I do first is I multiply 1 and 64, and I'm looking for things that multiply to 64 that add up to negative 16. After a little bit of thought, I get -8 and -8. So I've got x squared minus 8x minus 8x plus 64. I do my grouping, and so I get x minus 8. And I'm going to go ahead and factor out a -8, and I get x minus 8. So now this factors out to x minus 8, x minus 8, which means that these are my remaining two factors. I've got 3 factors here. Now they're all the same factor, but I've got 3 of them. The degree is 3. I'm done. If you really wanted to write this out like in a nicer way, you could have just said x minus 8 cubed. Now, this means that there's a triple root. So in the way of my real zeros, the rest of them, I already knew there was one at 8, 0. And the other 2, which there aren't any 2 others, it's really just one triple root, it's all going to be at 8, 0. I know that some of these examples felt like I was working through them really, really quickly. You'll see that we are going to be practicing this just for days in the next couple of sections. Good luck.